It's more on like just function calls and stack pointers and like how to just just a better overview because from what I understand, if we were to look at it in like in higher level code,
Yeah.
like when we create that stack pointer or like when we start to allocate to the stack, that's like the open curly brace, right? Like if you were to look at it from like the open curly brace and then deallocating inside like the closing curly brace.
It depends on which thing it is that's doing the stack calls, but yeah. If
Okay.
it's the function that you called that's dealing with the stack stuff, then yes. If it's the caller, so like if you're doing it in int main, it would be before and after the function call is where the stack operations occur.
I see.
Did you have a particular example you wanted to talk about, or just like
Oh
concepts?
yeah, a little bit of concept, and I'm pulling up the homework right now as well.
Okay.
Okay, so for homework 15 and no, problem 1, and it says that we need to use the stack, and I'm assuming that we have to create like a, from the main, like int main, and then we call int subtract, right?
So here you don't actually need to have the function call at all. You just implement the function itself.
Oh, okay.
So so here in the function, you'll notice that in order to store int result, the function utilizes register S7, right?
Yes.
Well, what do you know about S7? Or just the S registers in general?
Okay. The S registers in general, they're just to store variables, right?
Yeah, but all of the registers are used for that purpose.
Mhm.
Why do you think they're called saved registers?
Because we want to save it throughout our entire program, right?
For the most part, yeah. So if I use an S register while I'm just chilling in int main, and I do a function call, I expect that after that function call, that S7 has not been disturbed. That S7 has not been disturbed at all. That it retains its value that it was before my function call. So it's what's called a preserved register. So it's preserved through function calls, which is to say that if I call a function, I know that after the function call, none of my preserved registers will be altered. And S7 is one of those, as are the rest of the S registers. Um, and so what that means is that if a function is going to use an S register, it actually needs to save whatever that register was previously on the stack and then restore that value once it's done using that register. So, as an example, here in this function, you have a subtraction, and well, let's just actually go and do it. So, just note that because this is a function call, the parameters for your function are going to be stored in the argument registers A0, A1, A2, etc. In particular, we know that this has to be true. That the first parameter is going to be x, and that's in argument 0, and the second parameter w is stored in register A1. And we also know that S7 is where we're going to store a result. And so what we need to do now is we need to, well, start implementing the function and realize that because we're using S7, we have to save it. Because once we return from this function call that we need to make sure that whoever called us doesn't have to freak out about S7 being different than what they intended, than what they thought it would be. So the first line in your function call is going to be the label of your function or the name of your function. So I'll call that function subtract. And before we start messing with S7, because we're going to mess with it, we need to make sure we save it on the stack. So we have to save it, and the way we save something on the stack is we first decrement the stack pointer. And we decrement it by 4 because remember that RISC-V is byte addressable. So if you're going down an entire word, you have to go down by 4, an address of 4 units. And now that we've decremented the stack, now we can store something on the stack in this new position. So what I can do is I can say store a word, and that's because I'm writing to memory. I'm going to write a value to memory in the stack in particular. And the thing that I'm writing to memory is the contents of S7. Because I'm about to mess up the contents of S7, so I need to store them on the stack before I mess them up. And so here, this is just me storing it to the location of the stack pointer. So let's just pretend S7 was originally 5. All I've done here effectively is the following. This is where my stack pointer was originally, and there's some data stored on the stack. I don't know what it is. I don't want to mess with it. So I decrement by 4. That's this action here. So now our stack pointer is pointing to this location. And then I'm going to store the value of S7 to that location. So that just means that 5 is going to be written to the stack there. Okay, so any questions about that?
The one that you labeled the question mark, that's called the main stack frame, right?
Yes. If you were calling this function from main. If this was called from another function that wasn't main, then that would not be the main stack frame. That would be that other function's stack frame. But yes.
Oh, I see. Okay.
In general, the thing above it is just another stack frame from another function. We don't know what the function is, and we don't care. All we care about is not messing with it. So that's why we have to decrement by 4. Because this value on the stack pointer is something that belongs to that stack frame, because it could extend higher. I have no idea how high it goes. All I do know is that for me, I can't mess it up. I have to go one down, and then I can start writing values to the stack. Okay.
Just one more question, sorry.
Yeah, go ahead.
Okay, so you said that it's all within that program. So when we're looking at memory like this right now, it's all within the context of the program itself, and not every other program that's happening. Like, say, if we had like if our computer, like, we're not looking at like the entirety of that memory. We're just looking at the program's memory.
Correct.
Okay, thank you.
Yep. Okay, so the next thing we need to do is after we store this on the stack, we're free to mess up S7 as much as we want because it's saved, and we can restore it at any time we want later. So what we're going to do is I'm going to now do my actual function, which is the same as the one from last homework. So you just subtract the two values and store it in S7. So you take x minus w, x here is a0 and w is a1. You subtract the two and you just store that value into S7. So now S7 holds that value, and it's fine that we overrode whatever S7 was prior because we saved that on the stack. And so now I need to actually return from my function call. So I'm going to eventually do this. I'm eventually going to return back. But right before I return back, I need to do a few things. What do I need to do before I return to my caller?
Since you allocated, oh, Oh well, you would need to store your result into A0, right?
Yeah, I do. Yeah, so let's do that real quick. And I'm going to do it with a pseudo instruction. So I need to put the value I'm trying to return into A0. And S7 happens to hold a result, which is the value that I'm trying to return. So I move that into A0. Remember, you can just do this with an add immediate 0 instruction. So it's not too hard to turn this into a real instruction. And what would I have to do next? And I think you were going to say it.
Yes. Since you allocated from the stack, you would need to deallocate as well.
Yeah, so what would be the next instruction that I write?
Add immediate SP positive 4.
Okay. And then am I done now?
And I don't think so. I think you would need to load your word again.
Yeah, so what would I write?
Yes. Oh wait, wouldn't that mean that we would need to load our word first and then
Yes,
add immediate?
very
Oh,
good.
okay.
You have to do this in a backwards order from what you originally did. So here, I made space on the stack, and then I wrote something to that stack. I have to read from my stack before I can deallocate it. So this actually goes after. Very good catch. Load word, and then I have to load it into S7, so that's the register I'm loading it into. And then the place I'm loading from is just wherever the stack pointer is. So 0, SP. So same as this instruction, you're just doing a load word instead of store because you're reading from memory. And then you deallocate the stack. So in my picture, so SP1 is where I started, and then SP2 is where so this was the very beginning of the program, and then I allocated space, and that's where SP2 is pointed to after I allocated space. And then after I deallocate space, SP3 points to where SP1 was originally, the starting spot. And so now, I can say with certainty that 5 is actually still on the stack below me. But just keep in mind that this 5 is not allocated memory anymore. That just happens to be there because that's what I most recently wrote. But if, for example, right after this, main called another function and that had a stack, then that stack frame would then go to S5 or go to this address and overwrite whatever was in there before. And that's actually what we just did the first time. I just didn't say it. Originally, there was something here. We didn't know what it was, but I overwrote it with the number 5. And it doesn't matter what it was, because it wasn't allocated memory to the stack. So while the number 5 is still there, the stack does not have memory allocated to that particular address. And that would be the entire function. Any questions on that?
Okay, so going off of what you said about because it was not allocated to the stack, then it doesn't really matter before. Is that how like the operating system does it as well? Because like if we were to think about it as multiple programs, it would be all randomly accessible or randomly because of the RAM. But how does it know how much to jump off of without like so that it doesn't like touch other programs?
Well, it just depends on how you do it. So there's so one way that it's done is you do it with virtual memory, and you allocate like a chunk of memory to a specific program, and it just depends on how much the program needs. So you could allocate a megabyte of memory to a program, and then you just have the bounds, the lower and upper bounds, and you have that information freely available for all the other programs to know where that is. But typically, in that case, it's not used in terms of stack. That's used in terms of heap, which is where you just pick sections of memory. Instead of stacking them nicely on top of each other, you just randomly select areas of memory that aren't being used. Um,
Okay.
and so when you randomly select those areas, you just got to make sure, hey, I can't pick something that's already in use. And so there'd be like a lookup table, which basically you look at and say, okay, what's currently not in use? And I'll go look there for spaces I can take up.
So that lookup table stores things that have already been stored, right? Like in the program.
Yeah, it stores the addresses of. I can't remember the actual name of that lookup table. I think it's like the page table or something. Because when you allocate memory for a task or for a process, it's called a page. Or at least in virtual memory, it's called a page. And so when you allocate a page, the list of all the pages you've allocated is on a page. I think it's called a page table, and that would be the lookup table. But yes, yep.
Thank you.
Any other questions on this?
Oh no. After this, the first problem is done, right?
Yeah, that's it. All right. Are you cool if I erase this from the board?
Oh yes.
All right. Did you have any other questions for me?
Mm, no, because I would like to do the homework.
Like, just try it.
Yeah, just try it out first, and then maybe on Monday.
Okay, cool.
Thank you very much.
Yeah, you're very welcome.
How's your internship been going?
Right now, I'm learning how to use. I think I may have told you this before. I can't remember, but I'm mostly just learning how to use their tools right now because they are trying to have people who are very fluent in using their tools and are able to teach others how to use them and like explain it. And so they're having me learn how to use one of their. It's called A-Lint Pro. I don't remember what the A stands for. I think it's for the company name Aldeck, but Lint. Linting. Have you heard of linting your code before?
Oh yeah, that's like the formatting, right?
Not just formatting, but that's included in it. So like linting is just general like housekeeping stuff. So not only is it making sure your code is nicely formatted, but also that you follow like a specific set of rules with the actual functionality of the code and the way you code. So in terms of linting in hardware description language, which is like System Verilog, you have like a set of policies that you need to obey depending on what rule sets you care about. So as an example, just something I was looking at earlier today. I didn't know this, but apparently clock gating is not recommended to do on FPGAs. Have you heard of clock gating before?
I don't think I have.
Clock gating is useful for if you want to save power. So if you're sending a clock to a register, that register is actively burning up power. So what you can do is you can connect. Let's see if I can draw it. So what you can do is you can actually connect a clock, not directly to a register, but instead through an AND gate with an enable. And so basically all that's going to happen is that if enable's on, remember that the AND gate is just going to let whatever the clock is pass through. Because if this is 1, the AND gate outputs whatever clock is. So it's just going to behave like a normal clock, albeit with a little bit of a delay because of the AND gate, but that's not a huge deal. So it's going to behave like a normal clock. If enable's off, though, then this AND gate is always going to output 0, which means the register isn't going to actively burn power. It's called dynamic power when it's like switching and changing states. So you're basically cutting off the clock source to a register in order to save power. And that's very, very helpful for small power designs or minimal power designs, or like embedded systems or microcontrollers where you want to burn as little power as possible and be able to run your system for as long as possible. And I didn't know this, but on FPGAs, this is not good practice because of the way the clock lines are routed on the FPGA. There's like a clock oscillator, or crystal oscillator on the FPGA, and it sends a clock source. And the way that the clock source like signal gets routed in the FPGA makes it really, really taxing for the FPGA to route the AND gate with the clock into a register. So it just makes it really hard, and it basically makes it so you have to use excessive amounts of logic in order to get this on the FPGA. And so because of that, there's a linting policy, which when you have it enabled on the tool that they have on their software, basically gives you a warning when you try and make a clock-gated circuit. And so when you do a clock gating, it warns you and says, hey, you shouldn't be doing this if it's for an FPGA design. If it's for an ASIC design, which is just like a standard integrated circuit, have at it. But if you're trying to do it for an FPGA design, then you can enable that policy, and now you'll have both you and all of your staff in your company who are using the tool know that, oh shoot, I shouldn't have my clock. I shouldn't have a clock enabled. So that's like one example of linting. There's many more policies besides what I just said. That's like one of the like hundreds, thousands probably, depending on what rule sets you want to abide by and what your design needs and things like that. Did that make sense, or was I just was I just spouting gibberish?
No, that makes sense. The picture was really helpful.
Okay, cool. Yeah, so I'm just learning how to use that tool and like how to run stuff on it and do a bunch of different things. And I'm gonna be at the moment what's it called? I'm gonna be making videos to basically explain those topics for a little bit of time. So that's what I will be doing for the next few weeks, I think.
You're gonna post it to your YouTube channel?
No, not to my YouTube channel, to the company's YouTube channel, actually.
Oh, okay. Oh, okay.
Any other fun questions you have?
Trying to think.
No worries.
Could you give an introduction to like machine code? I believe the teacher is gonna do something more about machine code this next upcoming Monday.
Yep.
Okay.
Yeah. So again, when you are writing in a high-level C code, actual physical hardware has no way of interpreting that. And so the process is we take that code and we turn it into assembly instructions. Now again, assembly instructions, they're a level lower, but they're not directly executable in your processor. What you have to do is then convert those assembly instructions into just straight binary that the computer can actually interpret. And so it's the task of the assembly language's designer, whoever made the assembly language, it's their job to figure out a good encoding to make it so that you can have lots of different instructions and lots of different flexibility, but also make it so you don't need to have a whole lot of hardware to be able to understand the encoded instructions. And so essentially, in the case of RISC-V, every single instruction, this is for a 32-bit processor, every single instruction is represented as a 32-bit binary number. So as an example, this could be the hexadecimal code corresponding to some assembly instruction. We just don't know what it is. And so if you were the designer, you would have to figure out, okay, firstly, what instructions am I going to want my processor to be able to execute? How many registers am I going to have? Am I going to have, 1 unit of memory, 2 unit of memory, a whole bunch of stuff. And so from that information, you can decide exactly what you want your instructions to look like and how you want them to behave. And then from those instructions, you can decide how to encode them. So in the case of RISC-V, there's a few bit fields to be concerned with. And this depends on what type of instruction there is, and you can break them up into types. So the first two, basic ones, you'll go over a few more. Are R-type and I-type. So these are basically just your arithmetic and logic instructions, like add, plus, minus, multiply, or logical gates like and, or, all of those. The only difference between these two is that R-type instructions are instructions which have 3 registers that they execute on. So there's the 2 source registers that they read from, and then the destination register that they write to. Whereas I-type instructions are the same thing, except the second source register is replaced with an immediate value. So instead of having, so it's literally just the difference between this versus having this. So this is an R-type instruction because it has all registers, and this is an I-type instruction because it actually has an immediate. So that's what the I stands for. Does that sound good to you?
Yes.
Okay. There are other instruction types, but I'll just leave it at this for now. And I don't remember the exact encodings for them, but I'm gonna write I'm gonna write what I think it is, and we'll see what it is in just a minute. So for RISC-V, you have to tell it what kind of instruction you're going to be using. And so the type of instruction is determined by 2 fields, the opcode and the funct field. So the opcode is a 7-bit, field, which pertains data as to which instruction we're referring to. Now, in order to have enough instructions and enough richness in your assembly program, it's possible that maybe 7 bits isn't enough for what you want to store. That's enough to encode 128 different possible instructions, but that's using every single encoding. And so what you can do is you can use more bits if you want to express more instructions, or if you needed to. And so I think if I recall correctly, there's it's at the top of the sequence, but there's another field, funct, which basically corresponds to a specific type of instruction within a family. So the opcode typically corresponds to the family of instructions, so kind of like a general class. So maybe add and subtract might be in the same class as both being arithmetic operations, and they're very interrelated. And then the funct field would be able to tell you which of those 2 you're actually going to be using. So this tells me, okay, I'm going to be using add or subtract, and this tells me which. It tells me I'm going to use add or I'm going to use subtract. Okay, I'm going to go ahead and now I'm actually going to check the encoding. So R-type, encoding, RISC-V. So the encoding, or the instruction format encodings, are actually going to be given to you guys on the exam. You won't have to memorize them. You will have to understand what they mean, which is important, but you don't have to memorize them. Okay, so there is a funct3 field, but I was wrong. It's not at the top. It is actually further down. Let's see. There's 1, there's 2. Func3. So if I was looking at a generic R-type instruction, I would need to know a few things. I need to encode a few bits of information into my machine code. So the important bits are, which are my 3 registers that I'm actually using? So those are these 3 fields here. RD is this first register, RS1 is this this register here, and RS2 is this second register here. So that stands for the destination, and then source register 1, and then source register 2. Now in the case of R-type, you don't need any other information besides what am I doing. So what they do is they have the opcode, and then 2 funct fields. Again, because there are so many operations, you can subdivide them into categories. So you could have big overlying categories and then smaller categories, and then a specific function within that category. So that's what each of these fields are for, the opcode, the funct, and the funct7. So that's kind of the purpose of those. Now, depending on the instruction, like for example for I-type, it could be, or it is rather, that you have a different encoding because you're trying to represent different information. So let me actually write some bit fields here. This is 1107, this is 14 to 12. And just as a quick question, how many bits is RD?
In RISC-V, isn't that 4?
Well, from 11 to 7, if you just subtract, you don't get the full count. You have to count like the bit fields themselves. So you have bit 11, bit 10, 9, 8, and then 7. So that's actually 5 bits. Just like when we say in Verilog or System Verilog, you say 4:0, that's 5 bits, right? 4 minus 0 is 4, but the number of bits in that range is actually 5 bits. So same deal. So this is a 5-bit field. Let me go ahead and write that in for these. This is 7 bits. So this is 7 bits. This is 5. It's called funct3 because it's 3 bits. And then the source register is also 5 bits. 5 bits, and then this is 7. And so if we were to add all of those up, we would get, hopefully, we would get 32. So let me just double check my work. 5, 5, and 5 is going to be 15. And then you have 3 and 7 is 10. So that's going to be 15 plus 10 is 25. And then 25 plus 7, that's 32. So it is 32 bits. That's right. So I can go ahead and write the rest of these in. 15 up until, it's going to be 19, and then 20 up until 24. 31 to 25. So those are the fields of the bits, which each of these kind of regions or fields goes in. And depending on the instruction, so this is for R-type, if it's for I-type, you'll notice that instead of having 3 registers, I actually have 2 and an immediate value. So I need to be able to encode that immediate somewhere here. So I have to switch up the way that I encode it. In RISC-V, it happens that for I-type, the opcode, and this is true for every single instruction type, the opcode is always located in the bottom 7 bits. And that makes it really nice because in hardware, if you wanted to know what class of instruction you're dealing with, you would always just read the bottom 7 bits, and that would tell you everything you need to know, and you don't have to worry about what type of instruction you're doing. This is going to tell you what type of instruction you're doing, and then the hardware is able to decide what the rest of the bit fields means. So here, the opcode is always in the bottom 7 bits, and it's just going to tell you in more or less, it's just going to tell you what type of instruction you're doing. So this specifies, hey, I'm doing an R-type, I'm doing an I-type, I'm doing a J-type, as you'll learn some of the other ones, and there are others. There's U-type as well. So this is going to tell me my type, and then my processor is going to know what the rest of this is going to look like based off of that type given by the opcode. So for the I encoding, it happens that this is still RD. Ow. And then you still have a funct field, a funct3 field here. And RS1 is still there. But remember that we actually don't have an RS2. There is no second source register. And it happens that actually all of these bits here are used to encode the immediate. So instead of having an RS2, and also we got rid of RS7, or the funct7 field, we now have that to encode any 12-bit immediate we want. And so for any I-type instruction, you would figure out how to encode 7 in 12 bits of 2's complement binary, and you would put that number here. So it'd be all zeros, and then the bottom bits would be 111. And then you would put the binary encoding for register A1 here, the binary encoding for register A0 here. You would put the opcode, which corresponds to I-type, specifically the add I instruction here, as well as the funct field, which corresponds to add immediate here. And so all that we're really doing is we're just saying, I want to figure out how to encode my information nicely into 32 bits. That's all that machine code is. How do we encode our instructional information? That's everything. That's all that it means. The way you do it, and like the process for understanding how to efficiently do it, that's where the hard part gets in. There's a reason why the designers of RISC-V actually filled out the bit fields the way that they are, and you'd see that more as you go through the rest. You'll notice that once you get to some of the other bit fields, like there's what's it called? The UJ type, which has a lot of the bits for the immediate encodings swapped around a lot and like unordered. And it makes it seem very random as to why they would do it that way. And it happens that in that specific order, that the bits are kept in the same position between all the instruction encodings. And so it's easier on the hardware. You have less hardware to basically decode the instruction. And so in general, in a processor, you read the instruction from memory, and then you decode the instruction. So there are a few stages. There's the fetch stage, which is where you read the instruction from memory, and then you have the decode stage, which is where you basically interpret that instruction, you understand what it does, and then in the next stage, you execute it. So the next stage is the execution. And then after that, you have to do the memory stage, which is if you're going to be reading or writing to or from memory. And then after that, you have the write back stage, which is where you store your information back into your registers. And so that gets more into like CPE 300 stuff. Just in general, though, machine code, how do we encode our assembly instructions into binary? How do we do it efficiently? And then you'll learn the formats and like what these mean. So that's like the general like introduction to it. So any questions on that? Because I know I went over quite a bit.
Yeah. Could you go over the stages again? Sorry. So I was able to catch fetch, decode,
yeah.
execute, memory, and there were like 2 others.
So you have the fetch stage, you have the decode stage, you have the execute stage, the memory stage, and then you have the write back stage, or the write stage. So like I mentioned, the fetch stage, that just makes it so you're reading, because your instructions have to be stored somewhere, and they're typically stored in what's called a program memory, which can sometimes be the same memory as the one you're writing to when you do load and store words. It could be the same memory as that. The memory there is called data memory, but program memory and data memory could share the same actual like memory space. It's just you might have data memory in some of the addresses and program memory as the rest of the addresses. It just depends on how your architecture is and how the people who designed the system decided they wanted it to be. But anyways, your instructions have to be stored somewhere. So they're stored in a memory, program memory. And so you have to then basically tell the program memory, hey, I want to know what instruction is located at this address. Can you give it to me? And so then you have some delay associated with telling the memory to feed it, to give you a value, and then waiting for the memory to deliver it, and then receiving it and storing it. And so that entire stage of telling memory, I need an instruction, and then instruction basically fetching it and giving it to you, and then you storing it in a register, that entire stage is called fetch. So that's just getting the instruction from memory. At this point, I don't even know what I'm going to be doing next. All I know is that I'm getting an instruction. Now in the next stage, decode, I have the instruction, I have the 32-bit binary value corresponding to some sort of assembly instruction. Now in the decode stage, I need to decode that binary so the processor can understand what to do next. So I need to understand, okay, I'm going to look at my opcode, and that's going to tell me, oh, I'm doing an add immediate instruction. And then I need to look at RD, RS1, and RS2, and tell my registers which ones are going to be needed. So RS1 and RS2 are going to be fed to what's called the register file. That's just a fancy way of saying a collection of your registers. So you have your collection of 32 registers, and each of those 32 registers can hold 32 bits in them. And so RD, RS1, and RS2 are 5-bit values, because if you were trying to choose between 32 different things, you would need 5 bits to encode that much information. 5 bits have 32 different possibilities, ranging from all zeros to all ones. And so each register is associated with one of those possibilities. So the 0 register is associated with the value hex 0. So the actual encoding, if you used the 0 register as a source register, for example, in the encoding, all of these bits would be zeros. It would be 5 zeros, because that corresponds to the 0 register. The return address register is the next one. So if you ever say like JRRA and you're looking for the register in that encoding, it's going to be represented as 00001. So 4 zeros followed by a 1, and so on. So each of these is going to tell you, hey, which register from my collection of registers am I going to be using? And so because my instructions have 2 source registers, I need to feed it 2, well, it depends on the instruction, but at a maximum, I need to feed the register file 2 different addresses. One to correspond to the first register source, and the second to correspond to the second register source. And then the register file basically outputs the values of those 2 registers on wires. And that would be part of what you have to do during the decode. Or that would be part of what you have to do during the decode phase. Not the part of the register file actually putting it out on wires, but the part of telling the register file that it needs to output those values on the wires. Besides that, you also have to send, well, not all of them, but the opcode for sure, as well as your funct fields. You need to send those to a control unit, which is basically in charge of, it's like the brains. It decides what instruction you're doing. So I was able to just give these values to the register file directly, because the register file just needs to know which registers to access. It doesn't know what it's using them for, it just knows that it's going to be using them. But the rest of the bit fields tell me how the entire rest of my processor is going to work. So what kind of, what inputs I'd need for all my multiplexers to select between different lines, what operation my ALU is going to do, whether or not I need to write to memory or to write to a register or anything like that. All of that information has to be decided based off of the encoding here. And the person who decides what happens is the control unit, which is can be implemented either as an FSM or as a combination logic, depending on the way your processor is. It just depends, but generally speaking, for single cycle processors, like the ones you'll be going over in the beginning of 300, it'll be just purely combinational. Anyways, I'm going off on a tangent. Decode stage, you basically figure out what the heck it is your processor needs to do. In the next stage, which is the execution stage, your processor runs a calculation. So, for example, if you're doing an add instruction, the 2 things that got read out of your register file, which is your 2 register values that you cared about, those go into your ALU and then come out the other end as the result of whatever operation it was you did. So for an add instruction, it's going to add those 2, and the output of the ALU is going to be, well, the result of your calculation. So that's what the execute stage is. After the execute stage, which is like after the ALU and all whatever other hardware you have there, like shifters and stuff, after that you get to the memory stage. So this is where, if need be, you would write something to memory. So that's why it's called the memory stage, because you're either going to be writing to or reading from memory. And so you can either write the value that came through the execute stage to memory, or you could not. Either way, you have to go through that stage and then go to the final stage, which is the write back stage. So in the write back stage, either the output of the ALU, in the case of like an add instruction, or the output of your memory, if it was like a load instruction, would be fed into a multiplexer, and that multiplexer would run back into your registers, because you then need to write the value that you either calculated or that the memory gave to you, and you need to write that back to one of your registers. And so that's the write back stage. So, without like a diagram on the board, it's very difficult to see exactly what I mean when I say that kind of stuff. But if you just looked up, let me see. If you were to look at I can't remember what chapter. It's the chapter in your guys' textbook. I think it's chapter 7 where you begin to go over processor architecture. And for that one, you can see like an example of the processor with these 5 stages that I'm referring to, as well as kind of like them split into those 5 stages so you can see exactly what's going on. I'm going to see if I can find a good picture, and I can tell you what page it's on. Let's see. Not that one. Oh yeah, there we go. Okay, yeah, it is at the beginning of chapter 7 in section 7.3, where they actually design the processor. And I believe at the end of section 7.3 is where they have like the full... Yeah, 7.3.3, that's where you can see like most of the what's it called? Most of the processor architecture actually drawn out for you. And that's just like a basic processor architecture where you have a single cycle processor and you don't actually have all the assembly instructions accounted for. It's just like a start, a baseline. It's not a fully fledged processor with all the instructions you would want in your assembly language, but it's a start. Anyways, there's a lot to talk about when it comes to that, because not only is CP300 just about covering processor architecture, so is the next class after 404, which is just covering advanced architecture. And so is another graduate level class, just covering more advanced architecture. There's a lot to go into it, more than I can talk about in 4 minutes, but that's the gist of it, or like part of it, or an introduction, I guess. Any questions for me? Because I know I threw some stuff at you.
Yes. So when you say that it reads the opcode, so the processor needs to read from the 0-bit to the 6-bit first. So it's like that type of sequence, right?
Well, it's not that it has to read that first. When it reads something, right? When it fetches the instruction from memory, it then stores that instruction in a 32-bit register. So it has access to all of the bits at once. So what happens is everything goes in parallel. You simultaneously are sending the register source bits to your register file, as well as reading your opcode to then tell your control unit, you're reading the opcode into the control unit to decide what you're going to do with the other control signals. So it all happens at the same time, all within the decode phase. But in terms of like what we think sequentially, yes, we need to know the opcode first, and then we can get the rest of the information. But it all happens in parallel. Any other questions?
Yeah. When we're converting it into machine code, it ignores all white spaces, so that includes like any space or any carriage return. So does it just grab the first 32 stores and then does the process you said it, or?
Okay, so when you're encoding assembly into binary, the assembler, like you mentioned, it ignores white spaces, but the only thing that gets put into program memory is just this stuff. The way that you typed the code, the way that you typed the assembly code, unless it's syntax, the syntax is wrong, the tabs and spaces and comments, they have nothing to do with this at all. It's just the raw, what is this? And how would you encode it? So like the way you type it is unrelated. Not like languages like Python where like tabs and stuff matter. The assembler doesn't do anything like that. It's very basic. It just turns the instruction that you intended for on this one line into the exact encoding that it represents, independent of comments and all that other stuff.
And then it fetches that encoding and then does this thing, right?
The processor fetches that encoding, yes.
Okay. Okay.
Any other questions?
No more questions from me. Thank you very much.
You're very welcome. Oh yeah, just as a reminder, both for you and mostly for me, tomorrow no school because Nevada Day, so no office hours either. But I'll definitely see you on Monday.
Yeah. Have a great 3-day weekend.
Same, you too. You too.
Thank you. Bye bye.